Hello again. We're still on Chapter 11, Infinite Series. We're discussing Power Series, Maclaurin Series, and Taylor Series. And over the last couple videos, we have developed a list of known Maclaurin series, and here they are. Now we're going to be doing some algebraic manipulations or taking compositions of functions and using our Maclaurin series to find series for other functions. And so here we go. Keep in mind that if you are asked to find a Taylor series about a value a that is not equal to 0, you should not be using this list of known Maclaurin series, because if your center a is not equal to 0, it's not a Maclaurin series. So if that is your direction, which is come up with the Taylor series about, for example, a equal to 1, you would want to proceed with building a table of Taylor coefficients and forming a Taylor series around a equal to 1 and not using these known Maclaurin series. All right, so let's move forward and come down here to play around. So here I've got use known Maclaurin series to obtain a Maclaurin series for the given function. So let's take a look at this hyperbolic sine. I'm just going to rewrite this as an using my algebraic manipulations. That's the same as saying that's 1/2 times e to the x minus e to the minus x. Now I do know from my known Maclaurin series that e to the x is equal to n equals 0 to infinity of x to the n over n factorial. And I can proceed with writing out the first couple of terms just so we know what the terms look like from a pattern perspective. So when n is equal to 0, we have x to the 0 over 0 factorial, which is 1, x to the first power over 1 factorial, plus x squared over 2 factorial, plus x cubed over 3 factorial, and dot, 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 over 4 factorial, plus dot, dot, dot. Now, if I want to find an expression for e to the minus x, I'm using a composition of values, and using my known series, remember, e to the x, whatever that x is what I substitute inside my known series. So in this case, I'm going to still use my known series for e to the x, but instead of using just x, I'm going to replace it with minus x over n factorial. I'm going to use some exponent properties. I'm going to factor out that minus 1 to the n times x to the n over n factorial, so it can be easier to see what the sum of the terms look like. And so for n equal to 0, we still start off on a positive note, and we're still starting off with 1. When n is equal to 1, we have subtraction, and we have x over 1 factorial. And then we move back to when n is equal to 2, we move back to positive, and we have x squared over 2 factorial. When it's odd, we have a minus term, and when it's even, we have a positive term, and we can continue going. So now, when I form my hyperbolic sine, I have that that's equal to 1/2 times e to the x minus e to the minus x. That is the definition of hyperbolic sine. I'm just going to write out the first couple of terms and see where I go. So this is going to equal 1/2, and I see that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. And then I'm going to subtract. And remember, when we subtract, we're subtracting the entire series. And so I want to put this expression in parentheses. So I'm going to say that this is minus, and now I've got 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. And now I'm going to clear my parentheses, and when I clear my parentheses, I actually change the sign of each of the terms. And so here I go doing that. This is going to equal 1/4 open parentheses, and I have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus ... And now I'm going to remove and distribute the minus and remove the parentheses, and I end up with minus 1 plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus ... And now I want to start seeing what am I canceling, what collapses, and I get that 1 minus 1, I have plus 2, I have minus x squared and plus x squared over 2 factorial. I have plus 4 minus 4, and so I see that I am getting a series that looks like x 2x, and then I have plus 2 times x cubed over 3 factorial plus, and I can see a pattern here that my odd powers are maintaining existence in my series expansion. And then if I multiply through by the 1/2, I end up with x plus x cubed over 3 factorial plus x to the 5th over 5 factorial plus ... And then I can see that I have all positive terms, so I don't need a minus 1 to the n, and I actually can begin with n equal to 1, and I can say that this is from n equal 1 to infinity of x to the 2n plus 1, or actually I'll start from 0, because then if I start with n equal to 0, I get x to the 1st over 2n plus 1 factorial. Good. And that is my series expansion, Maclaurin series expansion for hyperbolic sine, and I began by just using definitions of power series expansions for e to the x and the definition of hyperbolic sine. So we can move forward with the next example. I'm just going to draw a new line over here. And remember that sine x cosine x, that is the same as saying this is sine x times cosine x. And remember that we have power series expansions for sine x, and we have one for cosine x. And remember the one for sine x from our table above starts from n equals 0 to infinity, and we have minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And we also have, and what does this series look like? We have that we start with 1, or we start with x, right? And we have that this is equal to x when x is 1. We have minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... With cosine, we have cosine as an even function. That's how I tend to remember which one has even coefficients or exponents and which ones have odd. Cosine's an even function, so we know that we've got x to the 2n in our series expansion. And we end up with n equals 0 to infinity of minus 1 to the n times x to the 2n over 2n factorial. And this ends up being starting with 1. And we have minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Good. So how would we put together a sine times cosine? Well, we kind of want to make an estimate, and since we don't really want to overdo this, just to demonstrate the idea, I'm just going to use a couple of the terms. So I can say that this is going to be roughly equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. And then times my cosine, and I'm just going to use a couple of those terms, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. Right? And that's what my sine times cosine is. And now I'm just going to expand the polynomial. So multiply. And so remember, that is going to be roughly equal to, and if I take each term and I multiply by this expression and then this term and I add it to this expression, this is going to equal x. And I'm going to go, this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. And then I have minus x cubed over 3 factorial, and I'm still going to multiply by 1 minus x squared over 2 factorial times x to the 4th over 4 factorial minus dot dot dot. And then I have that last fifth term, and I multiply again by that secondary, because this is just multiplication of polynomials, right? Minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot dot dot. So now I start doing my multiplication and doing my distributive property, and this is going to equal x minus x cubed over 2 factorial plus x to the 5th over 5 factorial minus dot dot dot. And then I have minus x cubed over 3 factorial plus x to the 5th over 3 factorial times 2 factorial minus x to the 7th over 3 factorial, 4 factorial, and then I have in that last one plus minus dot dot dot, or plus. And then I have here x to the 5th over 5 factorial minus times a plus is a minus, x to the 7th over 5 factorial, 2 factorial, and we have plus x to the 9th over 5 factorial, 4 factorial. Good? Plus, minus dot dot dot. And so now we want to start grouping like terms together. And so this is going to equal, we only have one term of x, and then I'll have plus, because we always want to do an infinite sum, so I usually go back to the plus, but I still see a negative here, so this would be negative 1 over 2 factorial. That's this one. And where's the other cube? I have this one, minus 1 over 3 factorial, but this is x cubed. And then where's my x to the 5th? I do have x to the 5th here, and that's going to be a plus. And I have 1 over 5 factorial. I have plus 1 over 3 factorial, 2 factorial. And I also have another plus 5 factorial, or 1/5 factorial. And this would be x to the 5th. And then we can proceed further with the others. But you get the idea of grouping our terms, and then you would want to reduce these fractions, because I'm not seeing a huge pattern here. So we want to reduce as fraction. Right, and here this would be 1/2 plus 1/6, and so we would have 3/6 plus 1/6 is 4/6 or 2/3, so this would be roughly equal to x minus 2/3 x cubed, and we'd want to reduce as fraction and write as fraction. Good. So remember, this is minus 1/2 minus 1 over 6, and so we would have minus 3/6 minus 1/6, and that's minus 4/6, and that's minus 2/3. Good. And so here we would have insert that fraction here times x to the 5th plus dot dot dot. Good. And that's how we would want to write the first couple terms. And here, not being able to establish a pattern, we want to just write our power series with the first couple of terms, knowing that we're going to get convergence because cosine and sine have those convergent series, and that multiplication of that convergent series is that. So again, here it says find the first 3 non-zero terms of the following series. I tend to like to write 3 terms of the first series, 3 terms of the second series, and then multiply them together here because we do have multiplication, and then hopefully come up with first non-zero terms. So again, we have e to the x, that's what we're going to be using here. And e to the x is n equals 0 to infinity of x to the n over n factorial. So e to the minus 2x, remembering that whatever x is what we're taking to the nth power. So in here, whatever minus 2x is, we're going to put that as the base of our exponent inside of our power series expansion. So we would have minus 2x to the n over n factorial. Simplifying that, or writing it in proper power series form, we would end up with minus 1 to the n, 2 to the n times x to the n over n factorial. And if we wanted to write out the first couple of terms for n equal to 0, we'd have minus 1 to the 0, 2 to the 0, which is 1, and 1 over 0 factorial is 1, and x to the 0 is 1. So we have 1. When n is equal to 1, we would have minus, and we would have 2, and we'd have x, and we'd have over 1 factorial. So this would be over 1. Plus, because when n is equal to, so remember this is when n is equal to 0, this is n equal to 1, this is n equal to 2, and we would have, and I'm just going to do the first 3 terms, so we have plus negative 1 to the second power times 2 to the second power, which is going to be 4, times x to the second power over 2 factorial plus dot dot dot, and just writing that simplified, I get 1 minus 2x plus 2x squared. Sine x, again, we have our known series, is n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. And for the first couple terms of the series, when n is equal to 0, we have x. When n is equal to 1, we have minus x cubed over 3 factorial. And then we have plus x to the 5th over 5 factorial minus dot dot dot. So those are the first 3 terms of those 2 series. And so when we put together our e to the minus 2x times our sine x, we're going to have an estimate that is equal to 1 minus 2x plus 2x squared plus, actually it should be minus, dot dot dot, times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot dot dot. And again, just like in the example that we just did, we're going to want to expand. So we're going to go 1 times this entire polynomial, infinite polynomial, times minus 2 times this, and then times 2x. So this is roughly equal to 1 times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus 2x times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and then we have plus 2x squared times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And now I'm going to expand my expression here term by term, and I end up with x minus x cubed over 3 factorial times x to the 5th over 5 factorial dot 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 And now I'm going to expand this one, and we get minus 2x cubed plus 2x to the fourth, but 2 divided by 3 factorial is going to be 3 because it's 2 divided by 6. So I can say that this is plus x to the fourth over 3. And then I have minus 2 times x to the sixth. So if I have x to the sixth here, and I know that 24 times 5 is 120, and 120 divided by 2 is 60. So I can say that this is times minus x to the sixth over 60, just for foreshadowing and simplifying. Dot, dot, dot. And if I expand this one, I end up with plus 2x cubed, and I still have minus. And again, I have x to the fifth, and 2 divided by 3 factorial is 2 divided by 6, which is 3, 1/3. And then I have plus, and again, I'll have plus x to the seventh over 60. Good. And when I go to collect my like terms, to get the first 3 non-zero terms, I'm just going to be looking for like terms to group them together. And I do see that I end up with the first term only has x. And then do I have any squares? I don't. I don't have any. I do have cubes. So I'm going to say plus, and I have a cubed term here. And I'm going to say it's minus 1 over 3 factorial. That's my first cube. The second one is minus 2. And then the third one that I have is plus 2. And I know that this is x cubed. And then I have the next one is I do see an x to the fourth. And so I do have one term here that is x to the fourth. And I have plus x to the fourth over 3. And those are my non-zero terms, and I don't need to do any more, so I just want to simplify this expression. So I have that e to the, what was it, negative 2x sine x is roughly equal to x, and minus 2 plus 2 is 0, so minus 1 over 3 factorial is minus 1/6 times x cubed. And then my next third term is 1/3 x to the fourth. And that's the first 3 non-zero terms, and I'm using my known Maclaurin series and power series expansions for each component, and knowing that I can multiply by multiplying polynomial terms. Good. F of x equal to tangent x involves the division of fractions, right? Because we have tangent x is going to equal sine x over cosine x. So we would want to write out the first couple terms and maybe just do 2 of them, or they do want 3 terms, so maybe we want to do 3 terms of each. So remember that sine x is going to be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial dot 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 divided by cosine, and cosine x is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus dot dot dot. Good. And when we have division or fraction division, we do take the b on the outside and put a on the inside of our radical, and so this is involving division of fractions. So that is how you would set this up. And usually when I'm just going to take the first couple terms, I tend to rearrange them into descending powers. So if I'm just going to use the first couple of terms, I'm going to write this as, sorry about that, x to the fourth over 4 factorial, and that was plus, and this is minus x squared over 2 factorial plus 1. That's in descending powers. And I'm going to do the same thing with the sine function, and I'm going to say that this is 1/5 factorial times x to the fifth. and we have minus x cubed, 1 over 3 factorial x cubed, and then we have plus x, dot, dot, dot. And so you want to do your multiplication, or you want to do your division, right? So you want to say, taking a look at this, going x to the 4th over 4 factorial times what gives me 1 over 5 factorial times x to the 5th. So I know that if I multiply by x here, right, I'm going to get x to the 4th, but I do want to multiply by, if I multiply by 4 factorial over 5 factorial, if I did that, my x to the 4th over 4 factorial times 4 factorial over 5 factorial times x, that's going to give me my x to the 5th over 5 factorial. So what does this actually equal? 4 factorial divided by 5 factorial gives me 1/5, right? So that's going to be my very first term. And remember, with long division, what do we put here? We put the top factor times the outside. And so what did I put on the top? I put 1/5 times x. And what's on the outside? X to the 4th over 4 factorial minus x squared over 2 factorial plus 1. And if I expand that out, I would get x to the 5th over 5 factorial. I would have minus x squared over 10, and I would have plus 1/5 x. And that's what I would put underneath here. I would have x to the 5th over 5 factorial, and I would put minus x squared over 10, and you don't want to line it up under the x cubed, but then you would say plus 1/5 x. And what do you do when you do division of polynomials? You subtract this, but you're subtracting the entire expression. So in order to change minus to a plus, we want to distribute and then collect like terms. So if we distribute here, this becomes a minus, this becomes a plus, this becomes a minus, and now we can collect our like terms, and the x to the 5th minus, or 1 over 5 factorial minus x to the 5th over 5 factorial is 0. We have 0 plus this, so we would have plus x squared over 10. And then taking a look at 5/5 take away 1/5 is going to be 4/5. And we would begin again, right? So we would want to drop down the next one, and we'd begin again. So we would be beginning with 1 over 6 x cubed plus x squared over 10 plus 4/5 x, and I'm starting again with this. X to the 4th times what gives me here, and it looks like I might need to have bigger powers there to get the first 3 non-zero terms. So I might actually, I should have probably gone all the way up to x to the 7th, or maybe x to the 8th, or x to the 9th. Better to start, because that way I'll probably get more terms, the first 3 non-zero terms. So it is a bit more difficult to do long division of polynomials, but you get the idea. It is an algebraic manipulation of your expanded terms, and you usually just want to use the first couple. All right, so I'm going to stop.